Today, we're popping the hood on Perovskite solar cells. We're going to anatomically deconstruct exactly how these complex molecular engines work, why they are absolutely shattering efficiency records right now, and what hurdles researchers are still sweating over to get them fully commercialized. Think of a solar panel like a vehicle. If the surrounding materials are the chassis and the wiring, the perovskite layer is the engine of light. It's the core where the actual magic of turning sunlight into electricity happens. Let's get into it.
Here's our roadmap for today. We're going to cover 1. The heart of solar cells. 2. The recipe for perfect absorbers. 3. Meet the perovskite family. 4. The mixed cation revolution. And 5. The future of solar materials.
All right, part 1, the heart of solar cells, the photoactive layer.
So to truly understand perovskites, we have to start with that photoactive absorber layer. This single layer basically dictates every important performance metric of the device: efficiency, voltage, stability, you name it. It essentially performs 3 highly precise mechanical steps. First, it absorbs sunlight across a massive spectrum. Second, when those photons hit, their energy generates what we call electron-hole pairs. Basically, a photon knocks a negatively charged electron loose, leaving behind a positively charged void, or a hole. And third, the material has to transport these separated charge carriers to the electrodes. It's a race against time, really, because if they recombine before reaching the electrodes, that captured energy is permanently lost.
And this comparison right here is exactly why the industry is losing its collective mind over this tech. Traditional silicon, the stuff dominating the market right now, requires an absorber thickness of over 100 micrometers, but a perovskite absorber, it needs less than 1 micrometer. Because it absorbs light so intensely, we can use a literal fraction of the material, which fundamentally changes the entire cost and manufacturing equation.
Moving right along to section 2, recipe for perfect absorbers, the physics.
You really can't talk about solar physics without talking about the band gap. It's basically the gatekeeper. It's the energy range that controls exactly which wavelengths of sunlight a material can capture. Now, to reach the absolute theoretical maximum for solar cell efficiency, which physicists call the Shockley-Queisser limit, a material needs a highly specific band gap. Most high-performance perovskites sit perfectly in this sweet spot, right around 1.45 to 1.6 electron volts. This is crucial because it aligns beautifully with the most abundant, energy-dense light coming straight from the sun.
It really is a classic Goldilocks problem. If your band gap is too large, the light just passes right through, you absorb less sunlight, and you get low electrical current. But if it's too small, your overall voltage drops, and there goes your efficiency. Perovskites are incredibly special because they hit that just right middle ground almost naturally.
But here's where it gets wild: defect tolerance. In traditional semiconductors, a tiny crystal defect acts like a deep trap. Think of it like a massive pothole that completely swallows a passing electron, instantly ruining the material's efficiency. But lead-halide perovskites, they are wonderfully forgiving. Their natural crystal imperfections usually just create shallow states. They're just tiny bumps in the road. The electrons can flow right over them, so these defects have a surprisingly small impact on overall performance. It's a huge advantage.
Let's jump to section 3, meet the perovskite family, the genetics.
It's super important to remember that perovskite isn't just one single compound. It's actually a specific crystal structure following an MAPbX₃ formula. Back in 2009, the most famous member of this family kicked off a total revolution. That was MAPbI₃, or methylammonium lead iodide. It showed us we could literally print highly efficient solar cells from cheap liquid solutions instead of using expensive high-vacuum chambers. Total paradigm shift, right? But it had glaring flaws. It degraded rapidly around moisture, its organic parts would essentially cook out under extreme heat, and of course, it contained lead. So researchers pivoted. They swapped out the methylammonium for Formamidinium, creating FAPbI₃. This gave us a better band gap and even higher efficiency. But it introduced a fatal flaw, known as the FAPbI₃ problem. At room temperature, pure FAPbI₃ is highly unstable. The atoms actually rearrange themselves into a non-photoactive yellow phase, where it basically just stops absorbing light altogether. Not exactly what you want in a solar panel.
Which brings us to a huge breakthrough in section 4, the Mixed-Cation revolution, molecular mixology.
To solve these massive degradation issues, scientists basically had to become molecular mixologists. The modern standard completely throws out the idea of using just one compound. Instead, the best cells today use engineered mixtures. They combine formamidinium, methylammonium, and purely inorganic cesium, creating a triple-cation perovskite, and then they mix in different halides.
By combining atoms of slightly different sizes, they effectively wedge the crystal lattice tightly together. It locks the structure in place, slashes the defect rate, and drastically boosts moisture and heat tolerance.
And honestly, the results speak for themselves. 26%. That is the certified efficiency benchmark that these mixed cascade devices are consistently crossing today. Hitting over 26% efficiency with a material you can essentially print from a solution, that is an absolute engineering triumph. Finally, Section 5, the future of solar materials, beyond lead.
So the efficiency problem is largely solved. Now the frontier is all about surviving extreme environments for decades and dealing with lead toxicity. When you look at the current landscape, the Fa/Ma/Cn's mix is sitting proudly at the top with high stability and huge efficiency. But look below that at the lead-free alternatives. Materials like the double perovskite have a great environmental profile, sure, but unfortunately they suffer from a poor band gap and just really low efficiency. Tin is the most direct replacement for lead, and it actually has a beautifully optimized band gap. But tin is a nightmare to work with. It oxidizes instantly in the environment, causing catastrophic degradation. On the flip side, one of the most exciting research directions right now doesn't remove the lead at all. Instead, it layers 2D and 3D perovskites together. The large organic molecules in that 2D layer act like a chemical shield. They passivate surface defects and aggressively block moisture, locking in that long-term stability without killing the efficiency.
And that brings us to the stark reality of the field right now. Even with the toxicity concerns, lead-based compositions just possess this magical, almost irreplicable combination of traits. Direct optimum band gaps, sub-micrometer absorption, crazy long carrier diffusion lengths, and that unmatched defect tolerance. Plus, because you can tune their band gap, you can stack them directly on top of traditional silicon to create ultra-efficient tandem solar cells.
The rapid evolution from simple, highly unstable crystals to these wildly engineered, moisture-resistant hybrid structures is easily one of the most exciting scientific journeys happening today. The core science is totally proven, so I leave you with this. As researchers dial in these 2D/3D shielding techniques in silicon tandem arrays, how soon are these molecular engines going to be manufactured at scale to actually power our global grid? It's going to be absolutely fascinating to watch. Thanks for joining me on this explainer today, and I'll catch you in the next one.